Hi. So I created these kind of sheets that are just kind of some summaries to hopefully help you guys. So there's one on the summary of the op-amp identification in my words, and then the op-amp rules, and then the summary of the op-amp circuits page. So I created a PDF, so these are on your handouts. And lectures notes at the very top of the section, there's a PDF of those 3 pages if you would like those. So today we're just going to do practice. So we're not going to learn any new concepts. We're just going to go through some practice problems with the op-amp. So with that, the summary of the op-amp identification, first step is to look at switch comparator configuration. So does it have feedback? Does it not? If you see it's a switch comparator, then you're done. And you just will analyze that based on the inputs, the positive side or the negative side. Whichever one is greater, it will go to the rail of that side of it. For the feedback, you need to identify then how many inputs and then identify which input terminals the inputs are going into. And then I tried to kind of summarize those. So one input, it's going to be inverting, non-inverting, or voltage buffer, voltage follower buffer. And so the inverting negative input, non-inverting is plus input, and then the voltage follower buffer will be the plus input. So the voltage follower difference between non-inverting and that one is that the voltage follower only has a pathway from the output back to the negative input. It doesn't have that other connection from that negative terminal pathway to ground. So that's the difference between those two. If you have 2 inputs, you're going to have an inverting summer, non-inverting summer, or a subtracting or difference. I guess I can't type. A difference amp. So either of those names. Difference amp. And so you'll have one at the positive and one at the negative. Okay, questions about identification of op-amps? Yes?
How do you know if it's a switch or a feedback again?
So on a feedback system, they always will have a pathway from the output back to an input. So in this case, it goes back into the input. So sometimes one of the confusing things is that here it's not drawn the power supplies, but in some circuits on a schematic, you may see the power supplies look like they end up getting back to the input through the power, but that's separate, so that will not be feedback. So that's one thing to note and be careful about. All right, other questions or wanting clarification? Okay, so the op-amp rules. So input terminals, you have 0 current into them. The output will act like a voltage source, and it's set by the input. So if you have a switch or comparator configuration, it's going to act differently than if you have a feedback configuration or feedback configuration. Sorry. So another characteristic that it does actually operate differently depending on those external connections. So if you have no feedback, it's going to take the internal gain, which is really large, so you always assume really large. Color. So assume this is large. And then it will take the positive side minus the negative side, and whichever one is greater, it will then hit the rail value of that one. So if it's 15 volts and this ends up being like a positive, then you'll get plus 15. If it's negative 15 is your other side and you get a negative number here, you'll get the negative 15. So depending on which one those are. Then for the feedback configuration, your VP or V positive is going to equal to your V negative, those 2 input terminals. And you use that then to solve for the outputs. So these are the summary of those configurations that we went through, where this configuration, the non-inverting configuration, inverting, and each of their gains as you go. One note I wanted to make on the non-inverting summer that we're going to go into is that on this equation, you have to be careful that, well, let me back up a second, I guess. Well, we'll go into the example, and then we'll go into that one. All right, any questions about these 3 pages that are supplied to you as far as the PDF of them? Okay, so if you want to grab those from the handouts and lectures module, they're just at the very top, called op-amp summary. So they're there for you guys to use. Okay, so let's look at this first example. And this circuit below performs the function V out is equal to A times some number A times V1 minus some number B times V2. So how will increasing if you changed R1? How will that change either A or B or not change it? So think about that for a minute. Try to get an expression for A and B, and then you can put your answer in. Tap on it. There we go. In the anonymous poll, if you would like. All right, good job. So identifying this, you see it has two inputs, V1 and V2, one on each positive and negative, so different subtracting configuration. So with that, then you say, okay, the equation, you can go back, look at the graph of it, or the table, and get that equation. Another thing is you may not see that this is one of those. So if you are able to remember how to do the non-inverting and inverting amps, you can actually solve any of the summers. So another way that I didn't show you last time that I wanted to point out is that op amps are really nice to do superposition with. So if you do superposition, if I start with superposition and I remove this source to start, get rid of it, there we go. That would make this a ground here. And then you can see like what configuration is this one. There you go. It's a non-inverting. And I need to know the voltage at this node, which is the voltage divider. So that node input is going to be the V1 R2 over R1 plus R2. And then I just take the inverting equation, which is this resistor over this one, plus 1. And again, if I don't remember that one, I can go back and put those equal and then do the current summation into the terminal at Vn. And remember this then, V out acts as a voltage source. So it would be Vn minus V out over R4 is equal to the Vn over R3. And then the Vn is equal to that V1 R2 over R1 plus R2. Okay? And then that equals that one for your V out here. So here's my 1. And then I can do the other source. So removing the other source, what is this configuration? It's just an inverting. And we know the inverting is just this resistor over this one and a negative. So negative R4 over R3 times that input V2. So then I sum them together to get the final. So if you're confused by the table, just knowing how to do the inverting and the non-inverting, you can actually solve all of the problems this way. So you just take out one source and then see what configuration it is, write that answer, take out another, or leave one source in, take out all the others, and then systematically go through each source so you have only one source applied at a time. Does that make sense? Does it seem easier this way? I'm seeing a lot of yeses. Okay. All right, great. Okay, so in this case, looking at the equation, if increasing R1, so if we increase R1, which is going to be there, it will reduce this number in front of V1. So increasing R1 results in decreasing A. So A will decrease. What about increasing R4? What change would that have to your V value? Here, let me write this. This was A V1 minus B V2. Yeah, so say we increase our 4, what happens to B?
It increases.
Correct. If we increased our 3, results in what change in B?
It decreases.
Correct. Does that make sense to everybody? Okay. Any questions on this? So with this one, you need to look at the actual output equation and then see the effect from that. Okay. Okay, so here is a, what do you call this? Here's a circuit. Go ahead and spend some time trying to solve for V out in terms of this Vs. So writing that equation. So this is a hint is to do superposition. So your first circuit would look like this one where you've removed the other two. The next one would look like this where you just have one source, or this one. So these would be your three circuits that you would have. So think about each of their contribution to the end. Give you guys another minute. So you're still going to have, so this is going to be a value that goes in and down. So you have two input sources, so this is actually different from this there. Because you have sources on both sides. So this accounts for one side, so you will just have to take this one, if you grounded that one, it's in superposition. And then that goes to this.
Oh, that's non.
It's non-linear. So you just kind of do that for each of those. Remember, it didn't affect, yeah. Don't know what happened to that. Okay, so there were some answers, so let's check and see if those that did get this got the right answer. So on this one, you have, you can identify that this first op amp becomes an inverting amp. And so the voltage becomes here fixed, and that's going to be the inversion of the input. So 10K over 2K times Vs. And again, if you don't remember that, you can rederive it, or you can go back and look here At this one, you see for the inverting amp, it's the RF, which is this resistor over this resistor. So that ends up being a -5 Vs, and that serves as the input to the next op amp. And again, you can identify this again as an inverting configuration, and it would be this resistor over this resistor. So V out would be a -12K over 6K, and then the input in this case is a -5 Vs. Yes.
I was just wondering, can you like kind of split the circuit in half and just use superposition on the first op amp, get that first voltage output, and then just treat the other op amp as like
The combined, yes, so this would just be a combined input to that.
yeah.
And then if you did superposition again on that op amp, it would be that as one, and then the other would be the plus side of it. So yeah, you could do it that way too. You should get the same answer. So whichever way you get through the superposition, it's fine to separate these up because we know that this node is a fixed voltage value. Is fine. Okay, so this is one answer. Any other questions on this op amp? Okay, so then the next one would be, that I chose was this one. And I identify that this first op amp with the source on the plus becomes now a non-inverting. So this non-inverting, again, it fixes this node. And so sorry, it becomes 10K over 2K plus 1 times 4. So that becomes 6 times 4 of 24. 5 plus 1, yeah. 6 equals 24. So that's 24 volts right there. And then that goes into an inverting. So the output here becomes -12K over 6K times this as the input, which is 24. So this now becomes a -2, 24 for 40, minus 48. So this would be a second part of your answer, and then the last part is this configuration. So there's no input on this first one, so that's going to give you a 0 volts like it's grounded there. So now we can just see there's only the configuration for this one, which is non-inverting, non-inverting. And so the output here is going to be a -12K over 6K plus 1 times 3. So that becomes 3 times 3 for 9 volts. So now we can add the 3 answers up. And our output is going to be 10 Vs minus 48 plus 9. So that becomes 10 Vs minus 39 volts. Yes.
You might have gone over it, but I'm confused on how you got the +1 in the 4-volt one and the 3-volt. How do you get the +1 like the 10K over 2K inside the parentheses?
So
Oh, because
it's a non-inverting amp. And I went through the derivation last time if you want to go look back at that video. You can write it either way, R1 plus R2 over R2 or the fraction. So the way I like to remember it is that amplification of the R1 over R2 or RF over RS, it's that feedback resistor over where the input, or the bottom one. So whichever way you like to remember that, or you can rederive it. The derivation is to take the currents in each of these, and the voltage at this node will be the voltage at the other side. And it would result, you can either again write it as R1 over R2 plus 1 or R1 plus R2 over R2. They're the same. Does that make sense? Did that answer your question? Okay. Other questions? Okay. It's a little bigger. All right, so it looked like it was very close for some people that wrote the answers. But remember, you have to take both. Need to solve for both of those 4 volt and 3 volts. Okay, any other questions on this one? Yes.
On that bottom one right there,
Uh-huh.
do you have a voltage going into the 6 ohm resistor?
The 6 kilo ohm?
Yeah.
So 0 volts is really like ground there. And so you don't have any voltage there at 0 volts.
Yep. And what type of amp then would be for that second op?
So it's a non-inverting because the input comes into the plus. So you're looking at that 3 volts as the input in there.
I didn't see the plus on
Yeah, and it's a plus on that bottom side. Does that make sense?
that. Yeah.
Okay. All right. Yeah, so it looks a little different because yes, you have an op amp there, but it really is just still 0 volts there. Or ground. And so you don't amplify that side, but the 3 volts still has to get amplified. Yes.
So just using the non-inverting and the inverting, we can solve any of the other configurations, just like using superposition
Uh-huh.
in this? Okay.
Yep. So I'll go through another example with one of the summers. And then you can see, yeah, you can do the same thing on those two. All right. Any other questions? Okay. All right. So this is the next example, which is a summer, and in this case, a inverting summer. But I also see like, oh, I have a V naught. Here it says to put V naught as 0, so that's actually going to be grounded. If it was not, you could actually treat this as an inverting summer and then a what on the plus, on the V naught side? If I grounded all of these 3, what would this configuration be? It would be a non-inverting again. I would put those 3 in parallel as one resistor, and then it would be a non-inverting configuration with 8K over these 3 in parallel plus 1 times that V naught value. And so I would then add that to the summer of the VS 3 volt and the 4 volt result. Does that make sense? Okay. So in this case though, just treat that as ground and go ahead and find an output equation for V out in terms of VS. And then we're going to talk about another little concept. That's the last one. actually go underground, so you can't compare it to those.
Okay, cool.
Okay, so a couple different answers, so let's see what the correct one is. All right, so I can use superposition on these. So superposition would put all of these, just gonna, I'm just gonna ground the V naught so I don't see it there. So these would be my circuits. So starting with VS in there, we get 1, 2, and 3 of them. So with this one, it looks like it's close to a inverting amp, but I have a signal coming in and then the 2 resistors in parallel. So I need to know the voltage here. To be able to solve this. So with this one, that voltage is going to be a division between, well, maybe it will be it's a little bit more confusing, I guess. So we'll put 0 volts here, and then we can do a node voltage on each of these. I'll put the currents going in, and then this current will be going out. So this will be Vs minus 0 over 2K plus 0, wait, 0 minus 0. How do I explain this one? Okay. I just went blank on this. 0 minus V naught over 8K. Yeah, I'm having a day, I guess. 2K times VS. But there should be a negative there. Why am I having a negative? Going in equals going out. Okay. It should be a negative. Somebody seeing where my error is? Nobody else is seeing it? Okay, I have an error in there
It's
somewhere.
supposed to be 0 minus Vs for that first term in your equation. Going from the node. 0 minus Vs over 2K.
the way I have it drawn, you could say it's Vs minus 0 over 2K. I've drawn a blank here. Minus, so that would give you the negative if you did it outward. Oh, you're right, thank you. Okay, yep. So it should equal each other, that's why. Okay. Could say these equal. Okay, they equal, or you could write it as the minus Vs over, or 0 minus, or minus going in, and then a 0 minus D01 over 8K equals 0. Either way, okay, thank you. I just did not see that.
Hey, Professor,
Yeah,
quick question. Couldn't you just use the inverting summing amp equation and just set the voltage, because the voltages for V2 and V3 are both going to be 0. V1 is going to be Vs, and then you just use like the equation that you treat, this, we get right there. I got the same exact result, just using that equation. The inverting summing amp.
yeah. There we go. Yes, you can do it that way. So that, yes, I mean, it's basically the same thing.
Okay.
So I was just showing redriving the equation again. But if you don't see that, then you can, you could do the same thing. With those zeros, then it's just going to be the RF over whatever resistor it is there. Yes.
In that diagram, it doesn't have a voltage source going into the positive of the op amp, but in our example we do. How do we solve for that?
So you could do them by the superposition again, where you get the answer for the inverting summer, and then you get the answer for the one with the positive, turns that into, let me draw that one. So if you have a voltage here, it will look like this. And if I combined each of these as an equivalent resistance, this would be a non-inverting summer, or not inverting amp. So your V naught here would be a minus 8K over R equivalent times V naught. Sorry, I'm doing the wrong one again. Plus 1. 8K over R equivalent plus 1 times V naught as a non-inverting. Does that make sense? So you would then find that solution and then add that to the summer equations.
Okay.
So in turn, these are each going to be a minus, so V naught 2 is going to be a minus 8K over 4K times 3. And then V naught 3 is going to be an 8K over 8K negative times 4. So you would then add those up. So this one is minus 4 Vs at 2, so 6 minus 6. And this one is a minus 4. So your output is a minus 4 Vs minus 6 minus 4, or minus 4 Vs times minus 10. All right, next time we're going to talk a little bit about the supplies themselves and the range that this would then be limited to with Vs.
Quick question. So I know when we should do this for like the feedback op amps, but what does it look like if it's a switch or a comparator? Like how do we know when we should just treat it like that?